Hello and welcome to the Jane's Lab tutorial on nonlinear least squares regression in Excel. Put together this tutorial to illustrate how to do specifically 4-parameter logistic curve fitting using the Excel solver package that can be installed after Excel has been installed on your computer. We're going to be using as a representative data set is an set of ELISA absorbance readings shown here on the top of the panel. The first group here is a twofold serial dilution of recombinant standards for the growth factor heparin binding epidermal growth factor, which was serially diluted down and then measured in technical duplicates here, replicate 1 and replicate 2. The absorbance at 450 nanometers is the true signal that develops as a result of the chromogenic reaction in the enzyme-linked immunosorbent assay. The absorbance at 550 nanometers on the right here, coinciding with each one of the twofold serial dilutions and each one of the replicates, is meant to, as a reference background absorbance to account for things such as non-specific autofluorescence or other signals because of the pallade or the height of the volume in the solution. And therefore, the first step before we do any of the nonlinear least squares curve fitting is to subtract this background reference from the ELISA signal, which is what I did here. So step 1, do the reference subtraction. Each one here is a formula subtracting the A540 signal away from the A450 signal, and that's iterated through all the rest of the serial dilutions for both duplicates. The right-hand side here graphs that corrected ELISA reading versus the known concentration of recombinant HBEGF in those solutions. The two technical duplicates are close to one another, and I'd like to emphasize that what is being shown here is on a log-log plot. The log-log plot will emphasize minor curvatures in that twofold serial dilution, which is what we seek to capture in the 4-parameter logistic curve fit. All right, step 2 is the logistic curve fitting. What I've done here is take those two technical duplicates and average them. That goes all the way down through twofold serial dilutions down to the 0 value here. The first step in doing nonlinear least squares curve fitting, and I want to emphasize at this point, what I'll talk about in the early stages is general to any nonlinear least squares curve fit. We'll talk specifically about the 4-parameter logistic model of the data, but you could use this for a hyperbolic function, any other type of curve fitting that you need beyond simply the pre-built ones that come with the Excel graphing software. Next, what one needs to do is build a model of the data that relates the concentration of HBEGF as the independent variable to the average reference subtracted absorbance signal shown in this column. And so what this is a bit more elaborate function which codifies the 4-parameter logistic curve fit. I sketched out that 4-parameter logistic function shown here. It has 4 parameters in it, A, B, C, and D. And in parentheses, what I've sought to define is what's the physical interpretation of each one of these parameters. The A is the implied maximum value of the dependent variable at infinitely high quantities of the independent variable. D, conversely, is the minimum value of that dependent variable at 0 independent variable concentration or input amount. The two other parameters in the middle here, parameter C is often referred to as the midpoint of the curve. What this 4-parameter logistic curve looks like is an S-shaped sigmoidal distribution. And so what C refers to is where the 50% mark would be in between the max value and the minimum value. And then finally, of the B parameter here, which is called either the Hill coefficient or the cooperativity value. What that refers to is the overall steepness of that S-shaped curve about the midpoint. Depending upon how large or small that B value is, you can have a flatter or a steeper S-shaped curve, all while still plateauing at the minimum and maximum values. This cooperativity can be positive or negative depending upon whether your S-shaped data is increasing as a function of the independent variable or decreasing. What this model function here simply does is it code in this equation using these parameters. And what I want to highlight is I'm using the row invariant shorthand here, the $, for all of the free parameters here that I don't want to update as I drag this function down. And so this is D, A, and D. A29 here refers to the concentration of HBEGF. That's the X variable. We do want that to update as we drag this function down through the rows, but we don't want C or B to update. So after having plugged this in one time, I can simply drag this down as a model for all of the data. And you'll see that the A29, A30, 31, 32 updates as I drag down, but all of the ones that have the $ in front of the row do not update as they drag down, which keeps those parameters constant. You can use the same $ in front of the column if there are other applications where you're dragging horizontally rather than vertically. Next, what we seek to do is calculate the squared error between the model and what the actual data was. And this is a straightforward function. Calculation from statistics will take the difference between the two values, the model and the data, the so-called residuals, and then square it to offset any pluses or minuses between the model and the data. And then our statistic here that we will seek to minimize sums up those squared errors for all of the values with which we can calculate it. And I'm going to get back to this one and why we have it grayed out right in a moment. And so when we perform a nonlinear least squares curve fit, the goal is to identify the values of A, B, C, and D that minimize that sum of squared error. Before we start using the solver that will do the optimization to minimize that sum of squared error, we should try to get these parameters a bit closer to what the data looks like, because what the software is going to do is perform an optimization where it's going to nudge each one of these A, B, C, and D values and look to see how the sum of squared error changes. The closer you are to the true minimum, the faster the optimization will go, and the less likely the solver will run the danger of falling into some other local minimum or running off the rails in the optimization and giving you the sense that it might not be working, when in fact what you did was just start with a set of parameters that were too far away from the global minimum. So what I'll do here is try to make some inferences what I think are that max value. Well, the max value here of 1, maybe that sounds okay, but this min value is too high. I think that this is probably going to be around maybe 0.05. You can see how that changes the shape of the distribution. It's also going in the wrong direction, and the reason why it's going in the wrong direction is because this cooperativity value is positive rather than negative. If I set it to -1, now I can start getting a hint. Maybe I have to change what this midpoint. I'm going to increase this midpoint to maybe 100. Okay. Here now, if I put this back to 1, you see that's a decreasing function with the increases in HBEGF. But if I change it to -1, now we're getting something that's rather close already. Looks pretty good to what the actual data are. It's because we had this negative cooperativity, and the value here is a 0. You can't take the square root of 0, so this will throw an error, which is why we will omit it from the sum of squared error calculation. And this is fine because this 0 value is baked in, if you will, in that D parameter. We'll probably get something that's very close to what that zero value looks like once we do the optimization. And so we have something that looks relatively close here. Maybe I'll increase this a little bit to illustrate how it will converge. Now what we need to do is minimize this sum of squared error value. To do this, we need to install some add-ins in Excel, which you can find under the Tools menu at the very bottom here. Excel add-ins. It's unclear to me why these don't simply come pre-installed in Excel, but they're on every version of Excel. They just need to be installed separately after Excel has been installed. The analysis Toolpak is a good thing simply to have. This contains software for ANOVAs, t-tests, and so forth. The one that we're going to use immediately today is the solver add-in. Click OK. Nothing appears to happen. But if you wait a second and then go up to the tools, now we have a data analysis and a solver packages that we can call to help us with the 4-parameter logistic fit. So I'm going to call the solver. Now a window comes up. Here is first thing we need to do is set what's called the objective function for the optimization. And that objective function for us is the sum of squared error. You simply click on the element in the Excel spreadsheet. Go back here. We want to set that to a minimum value. It's not going to be possible for us to get it to exactly 0, but we should be able to find a minimum. And the hope is that that minimum is the best, is not a local minimum, but the global minimum that's the best fit for the data. And then the way in which the solver will find that minimum is by changing a certain number of cells that are allowed to be altered to improve the objective function. Those are the 4-parameter logistic coefficients here, which we simply highlight. If there are constraints to any of these, for these are effectively unconstrained, but in certain circumstances, one of these parameters may need to be greater than or equal to 0, in which case you could say something like this, greater than or equal to 0, or greater than or equal to another cell value, and those will factor into the calculation. We don't need to do that, but I just show it for completeness. And then the next thing here, the default when this add-in comes in, is that if variables are unconstrained, make them non-negative. We don't want that to occur here because recall that B parameter is a negative value based on the nature of the curve that we're trying to fit. Thus, we will unclick that radio button. There are a number of different solving methods here depending upon the type of optimization that's being formed. For most purposes here, a simple nonlinear least squares curve fit, the default nonlinear engine that's shown here is sufficient because you are expecting a smooth, albeit nonlinear function to perform the optimization. Once we have this all set up, we simply click Solve. And it says that the solver has converged on a solution. If you go back and look, you'll see that the sum of squared error is substantially smaller than it was before. The parameters have updated to a different set of values. And when we click OK, now we'll see that the model is almost perfectly superimposable on top of the data. These now are our best fit parameters for the 4-parameter logistic curve fit as given by these data. I don't have it on this Excel spreadsheet here, but if we had unknown values where we observe a reference subtracted absorbance where we want to infer the concentration of HBEGF in that sample, straightforward thing then to do is use the inverted 4-parameter logistic curve fit, which now solves X in terms of Y rather than Y in terms of X, to back out inferred HBEGF concentrations in the data. And this could put in exactly as the functions shown up here, but with this functional form relating A, B, C, and D to X and Y. And that's everything for nonlinear least squares curve fitting in Excel.